Last problem, 8.4. We have the NMOS current source or current sink circuit, and for this particular circuit we have Q1 and Q2 with different aspect ratios. So Q1 is L1 W1, and for Q2 we have a width that's 5 times the width of the first transistor. Okay, we also have a reference current of 20 microamps and a V overdrive of 0.2 volts. So in part A we need to find what's the value of I naught for these conditions. Okay, so there's one equation that relates the output current based on the reference current. That depends on the aspect ratios of each one of the transistors. So basically that's an important equation, because if we change the dimensions of each one of the transistor, we change the relationship between the output current and the reference current. Okay, so the equation that dictates this relationship is, so it's I naught over I reference, so the reference current, and that's basically the ratio between the aspect ratios of, so this subscript 2 means for the second transistor, and here it basically means the aspect ratio of the first transistor. Now we know the reference current, so I naught is equals to that 20 microamperes. Now if we substitute W and L for each one of the transistor, for transistor 2 we have L2 that is equals to L1, so, and W2 that's equals to 5 times W1. So this is the same as times 5 W1 divided by L1 divided by W1 divided by L1. So basically W1 here, L1 cancels with these W1, L1 here, and then we have that the output current is 20 microamperes times 5, and that's 100 microamperes. So in this case, for a reference current here of 20 microamperes, because Q1 and Q2 have different ratios, and so in like specifically this case we have Q2 with a width of the channel 5 times larger than the width of the first transistor, we get a current that is 5 times the reference current here at the output. Okay, so we control that relationship between by changing the aspect ratio of the transistors. Now what's the minimum value of V out? So remember that V out, the minimum V out should be always greater than the overdrive voltage, because we need the transistors to operate in the saturation mode, right? So if the V overdrive is given as 0.2, the minimum value of V out is 0.2 volts. Okay, because remember from that curve we have like several curves here for different VGS, and then we have this particular dashed line here that defines those edge of saturation operation, and this particular point here is actually VDS equals to V overdrive, and because V out here is actually the voltage at the drain here, and Vs here is grounded, or VDS is actually VD, which is our V out. So we need that to be true again, right? So just this is VDS and this is ID. Okay, and here we have different VGS, different VGS. Okay. Now for part C, given a threshold voltage of 0.5, right, For what V naught we get I naught nominal. So for what value of V naught we get this I naught nominal, that is 100 microamperes, right? So first we need to define VGS, okay? So we know that VGS minus the threshold voltage is equals to the overdrive voltage. This is supposed to be a V. So VGS is equals to V overdrive plus the threshold voltage, and that's equals to 0.2 plus 0.5. So VGS is 0.7 volts. And we must have, now let me first give you the equation. So I naught is equals to the ratio, so I'll call WL2 divided by WL1 times the reference current, right? Times 1 plus V out minus VGS divided by VA. Okay, so that's the equation that gives us the value of I naught. So if we want to have the nominal current I naught, let me go back here. Remember that the nominal current is defined by the reference current times the ratio of the aspect ratios, right? So it's this part here. So for us to have this 100 microamperes here, we must have this entire thing here equals to 1, right? Because then we have the I reference, which is 20 microamperes, times the ratio of the aspect ratios, right? Which is 5. And that gives us the nominal current. And for this here to be true, this factor here must be equals to 0, right? So for that to be 0, VA, we know it's 20 volts. So we need V naught minus VGS equals to 0. And in this case, V naught should be equals to VGS. So if we calculated VGS for that particular condition, for that particular threshold voltage, we must have V out equals to 0.7 volts. Okay, because if it's 0.7 volts, then 0.7 here minus 0.7 from VGS gives us this factor here equals to 0, and then this entire thing here multiplies by 1, and then we get the nominal current. For part D, if we have a change in the output voltage of 1 volt, what's the change in the current, output current, if we consider an early voltage of 20 volts? So we know that delta I naught, so the change in I naught, is equals to delta in the output voltage divided by VA from the second transistor, right, times I naught. So this gives us a delta I naught that's equals to, so the change in voltage is 1 times I naught, so we are considering the nominal current, divided by the early voltage, that's 20. And this gives us a change of 5 microamperes. Okay, so if we change delta V naught by 1 volt, we change the output current by 5 microamperes, and that means that the new current I naught new, so after this change, is that 100 microamperes plus those 5 microamperes. That's 105 microamperes. Okay,